Welcome back. In our previous classes, we were discussing about the rules of differentiation or the easy tricks which we could make use when we perform the differentiation over a function. So we have seen till the quotient rule, and the next rule is generalized power function rule. Generalized power function rule. So we have seen that we have seen a power rule, right? Like d by dx of x to the power n equal to n x raised to n minus 1. Right. So the generalized power function rule is somewhat similar to this, but with a slight difference. Let g of x be a differentiable function, and f of x be another function which is defined as f of x equal to g of x all raised to n. So g of x is a differentiable function, and f of x is another function which is defined as the nth power of g of x. Then f dash x or d by dx of f of x is defined as n into g of x raised to n minus 1 into g dash of x. Right. This actually comes from another rule which is called the chain rule, which we will discuss soon, very after this. And your textbook actually describes this generalized function rule for some reasons, and for that reason we are obliged to discuss this prior to chain rule. Okay, so this is how we differentiate a function which can be expressed as the power of another function. So if g of x is a differentiable function and f of x is the nth power of g of x, then f dash of x equal to n into g of x raised to n minus 1 into g dash of x. See, let's see an example. Let f of x equal to f of x equal to x square plus 7 whole raised to 4. Find f dash of x. Right, we will make use of the generalized function rule here, power function rule. So f dash of x, see, we can consider x square plus 7 to be the g of x here. Then f of x is nothing but g of x raised to 4. If it is the case, f dash of x is n into, that is 4 into g of x, or what is g of x here? X square plus 7. We don't need these two brackets. X square plus 7 raised to 4 minus 1, which is 3, into g dash of x. G of x is x square plus 7, which is a quadratic function. So the derivative of x square plus 7 with respect to x is 2x. So that is 2 into 4, 8 into, or 8x into x square plus 7 whole cube. We need not simplify this anymore. Right. So this is the derivative of f of x equal to x square plus 7 all raised to 4, and this is how we use generalized power function rule. Next comes the chain rule. See, the generalized power function rule and a lot of other rules are derived from chain rule. Suppose we have two functions, say g of x and h of x. Both are differentiable. Alright, both are differentiable, and we define a function f of x to be the composition or the function of another function, or g of h of x. Right. Instead of x in g, we pass h of x as the argument. Right. So f of x equal to g of h of x. If it is the case, then the derivative of f dash of x is defined as g dash of h of x into h dash of x. G dash of h of x into h dash of x. See, you can observe that the generalized power function rule which we have seen a little ago is actually derived from this, where g of x is taken to be x raised to n. Then g of h of x will be h of x all raised to n. And g dash of h of x, see what is g dash? G of x equal to x raised to n, so g dash of x is nothing but nx raised to n minus 1, so g dash of h of x is n h of x raised to n minus 1 into h dash of x, which was the generalized power function rule which you have seen a little ago. Right, so this is the statement for chain rule. And now let's see an example of chain rule. Let f of x equal to root of 8x plus 9. 8x plus. See, this can be solved using the generalized power function rule as well, but for now we use the term chain rule. That's it. So find the derivative f dash of x. See, f of x equal to 8x plus root of 8x plus 9 can be simply rewritten as 8x plus 9 all raised to half. Right. Now this has come to a power form. Then now we can use the generalized power function or the chain rule as f dash of x equal to n into 8x plus 9 to the power n minus 1, right? 1 by 2 minus 1 is negative 1 by 2. So negative 1 by 2 into derivative of 8x plus 9. See, 8x plus 9 is a linear function, so the coefficient of x will be the derivative, so into 8, which means 4 into 8x plus 9 raised to 1 by 2, or 4 divided by root of 8x plus 9. Right. So this is how we use chain rule. See, as the power function rule is derived from the chain rule, there's no point in explaining this separately for chain rule. But still, keep in mind how do we use the chain rule. Right. See, all these rules of differentiation are actually derived from the very basic definition of derivatives. Let's see an example. Suppose f of x is given as g of x minus h of x. Right. Then we have the rule for sums and differences as f dash of x equal to g dash of x minus h dash of x. Let's try to prove this. So we'll use the basic definition using the limits for derivatives. So we know that f dash of x can be defined and is defined and can be evaluated sometimes as limit, say some delta x. Let's use delta x instead of h here since we have a function h. Delta x tends to 0. F of x plus delta x minus f of x divided by delta x. Right. If it is the case and we have f equal to g minus h. Right. That's how we defined f. If f is equal to g minus h, then f dash of x equal to limit delta x goes to 0. Instead of f of x plus delta h, we will be having f of x equal to g minus g of x minus h of x. So instead of f of x plus delta x, we can write g of x plus delta x minus h of x plus delta x minus, instead of f of x, we are supposed to write g of x minus h of x all divided by delta x. Right. So this is equal to limit delta x goes to 0. we'll just open those brackets and make a rearrangement. Okay, so g of x plus delta x. See, we'll have a negative g of x here, so we'll write it here, negative g of x minus, let me use the bracket, h of x plus delta x. See, we'll be having a positive h of x here, negative into negative h of x. So we'll be having a positive h of x, and using this bracket and negative, we'll be writing minus h of x here, divided by delta x. Now we can separate this limit as, using the properties of limit for the products, limit delta x goes to 0, g of x plus delta x minus g of x divided by delta x minus limit delta x tends to 0, h of x plus delta x minus h of x divided by delta x. See, what is this? Limit delta x tends to 0, g of x plus delta x minus g of x by delta x is nothing but g dash of x. See, this is how we define the derivatives. Minus, this is nothing but h dash of x. Right. So we had, we started with f dash of x and then g dash of x minus h dash of x, and thus h dash of x is g dash of x minus h dash of x. Right. So this is how we can make use of the formal definition or the fundamental definition using limits of derivatives to actually derive the rules of differentiation. This is not just for sums and differences, but all other rules can be derived from this. The next idea is about higher order derivatives. So we have seen what are derivatives and how to perform the operation differentiation to find derivatives. So now we think about higher order derivatives. So what are higher order derivatives? See, suppose we have a function f of x, right? And we perform the operation differentiation and find the derivative f dash of x. This is called the first order derivative, and this is again a function of x, right? So we can think about differentiating it once again. See, just like f of x, f dash of x is again a function of x. As in the case, if we have say f of x equal to some sin x plus x square, then the derivative f dash of x is cos x plus 2x. Again, this is a function of x, right? So we can think about differentiating it again with respect to x, and the derivative of first derivative of f may be called the second derivative of f, or the second order derivative of f, and denoted as f double dash of x, right? Or that can again be differentiated to obtain f triple dash of x, and again to obtain f4 of x. See, from fourth order onwards we use the number. It's a convention that to have lines or these dashes or primes a lot of times may be cumbersome. So to avoid that, we use numbers from fourth order onwards. That's a custom. And these all can also be notated using that d by dx symbol. So f dash x is nothing but d by dx of f of x, or df by dx, and f double dash of x is notated as d square f by dx square, and f triple dash of x, or the third derivative or the third order derivative of f with respect to x, is denoted as d cube x by dx cube. Sorry, d cube f by dx cube. Right. So again, you may observe either notations in your questions and in your practical applications. So how to find the second order derivative of a function? Simply find the first order derivative or simply differentiate once and again perform the differentiation on the first derivative. So performing differentiation twice will give you the second order derivative. Similarly for other orders as well. Right. So if you want, we can have a look at an example. So find the second order derivative of, or the third order derivative of f of x equal to 4x cubed minus 9x square plus 5x minus 7. So using the properties of derivative which we have seen, f dash of x is, what is the derivative of 4x cube? Derivative of 4x cube is 4 into, see, we have a form of x raised to n. So n into x raised to n minus 1. So this will be f dash of x equal to 4 into 3 into x square. So it will be 12x square minus 9 into 2 into x raised to 1. So it will be 18x plus 5x. The derivative is 5 and minus 7. The derivative of a constant is 0. We need not write it again. So we got the first derivative. And what about the second derivative? Differentiate the first derivative. So we have 12x square. So the derivative will be 12 into 2 into x raised to 1. So it will be 24x minus 18x will have the derivative 18 and plus 5 will be vanished. Or the derivative of the constant is 0. So what is f triple dash of x? Again 24x will have the derivative 24 and negative 18 will be having a derivative 0, right? So what is the fourth order derivative of f, which is the derivative of 24, which is 0, right? So this is how we perform the differentiation operation multiple times to obtain the higher order derivatives. This may come intermittently in your practical application, either in physics, chemistry or economics or wherever, right? So take care of this. The next is about implicit differentiation. It's another technique for differentiation. Before going deep to implicit differentiation, we need to know what are implicit functions and explicit functions. So what are implicit functions and explicit functions? So usually we denote a function as y equal to f of x. This has a sense of meaning, or a sense that we have an equality sign and the terms of y are on one side and the terms of x are on other side. As in the case y equal to x square, y equal to sin x plus 3 cos x plus 7x cube, right? In all these cases, we have the terms of y on one side and the terms of x on another side of, or on the other side of equality. But this may not be the case always. We may have functions of the form, say 3x square plus y square plus 7xy equal to 92, or maybe some x plus y, right? We can have functions of this form as well. In case, in several cases, we can solve this for y and we can convert this to this form. But there may be cases where we cannot convert this to this form, and those functions which can be expressed in this form are called explicit functions, which means just simply literally means the terms of x and y are explicitly written on either sides of the equality, and those functions of this form where x, y terms comes intermittently are called implicit functions, right? So we know how to differentiate explicit functions. To find dy by dx, we just differentiate everything on the right side of the equality with respect to x. But that may not be the case for an implicit function. We cannot simply differentiate everything on the right and find the derivative of y with respect to x. This definitely gives a relation between x and y, but not as a simple function we have seen so far. So the technique used to find here, to find the derivative of y with respect to x is called implicit differentiation. So more than going to the deeper theories, it's better to discuss implicit differentiation with an example. Right, so let's choose an example first. Consider the equation, let it be a simple one first. 4x square plus 5y cube equal to 39. Find dy by dx. Find dy by dx using for the given function 4x square plus 5y cube equal to 39. So it involves two steps. First step is to differentiate throughout the equation. With respect to x. Okay, so let's differentiate term by term. So what is the derivative of 4x square? Or what do we do here is d by dx of 4x square plus d by dx of 5y cube. See, when we differentiate with respect to x, we identify or we consider y as a function of x. So y is not just y is actually y of x, right? So we consider y as a function of x, even if we don't write it here, equal to d by dx of 39. So we differentiate every terms. And let's simplify it. D by dx of 4x square is 8x. We can use the power rule. Plus d by dx of 5y cube. So 5 is anyway a constant which can be taken outside. Derivative of y cube of x. See, actually we make use of chain rule here, but not without going that deeper. Differentiate y or y cube as 3y square and multiply with dy by dx. This is actually the chain rule here. Is equal to d by dx of 39 is 0. See, whenever we have a y, we have to write dy by dx. Remember that. We are actually using the chain rule. If you don't remember that, whenever you have a y, write a dy by dx. That's not actually the theory. We are making use of chain rule here. But if you fail to remember that, at least keep in mind that whenever you have a y, just differentiate it and designate with the dy by dx. Right. So simplifying this, we'll have 8x plus 5 into y, 3 into y square. So it will be 15 y square dy by dx. Now we can solve this for dy by dx as 15 y square dy by dx equal to minus 8x. So dy by dx is dy by dx is equal to minus 8x divided by 15 y square. Right. So we found the dy by dx. So the derivative of y with respect to x. So what were the two steps involved? First one, differentiate throughout with respect to x, keeping y as a function of x. The second step was to algebraically simplify this or solve this to find dy by dx. Or find dy by dx by solving or rearranging, simply rearranging and performing simple algebraic operations. So remember the two steps are, the first one is to differentiate throughout the equation with respect to x, keeping y as a function of x. And the second step is simplify for dy by dx. Right. See, let's see another example here. One more. Consider the function x cube y raised to 5 equal to 9. Find dy by dx. This is a little more tricky since x cube is a function of x and y raised to 5 is again y is a function of x. That's how we differentiate. So we have the product of two functions of x here. So to find the derivative, we'll have to perform the product rule. Right. So the step 1 2 is to differentiate throughout. So dy by dx of x cube y raised to 5 equal to d by dx of 9. So let's make use of product rule here. Product rule was actually given as the first function into derivative of second function plus second function into derivative of first function, right, is equal to d by dx of 9, which is 0. So simplifying this, x cube into derivative of y raised to 5 with respect to x. As we have discussed before, we'll just use the power rule here, 5y raised to 4 into dy by dx plus y raised to 5 into d by dx of x cube. We know how to do this. 3x square equal to 0. So if we simplify this, we'll have 5x cube y raised to 4 plus y raised to 5, 3 y raised to 5 x square equal to 0. And now we can, we have a dy by dx here, right? dy by dx equal to 0. Now you can try to simplify this for dy by dx. So why can't we cancel out an x square throughout? So an x will be left here. And cancel a y raised to 4 throughout. So a y will be left here. So which means 5x dy by dx is equal to 3y. Right. Then simplifying it again, dy by dx will be is plus 3y equal to 0 equal to dy by dx equal to minus 3y. Since this 3y can be taken to the right side of equality, and minus 3y divided by 5x. Right. So the derivative of y with respect to x is minus 3y by 5x. Okay, so this is how we make use of implicit differentiation to find the derivative of y where x and y are not explicitly given or given as an implicit function. Right. Now, let's see a few practical applications or examples of practical applications of derivatives. I hope you remember we discussed about the marginal cost and marginal revenue. Right. The marginal cost and marginal revenue were actually the derivatives of cost function and revenue function. And using the formal definitions with limits, we found the marginal and revenue functions of certain cases. For now, suppose we have a firm with the total cost function C of x is equal to 0.001 x cube minus 0.05 x square plus 7x plus 6500. This may look a crazy function, but still this depicts the cost function of a function, of a company where x is the number of products produced. X is the number of products produced. So if you give x equal to 1, this will give the cost of producing 1 unit, and if you give x equal to 10, this will give the cost of producing 10 units. Right. So now let's find. So the question is to find the marginal cost. The marginal cost for the 14th product. Right. Marginal cost for the 14th product. So let's find the general marginal function for marginal cost function. So the general marginal cost function is the derivative of cost function, which is dc by dx, since c is the function here. So how to differentiate this? This is a constant into x cube. So let's take the constant out. See, we differentiate term by term. That's how we perform differentiation over a polynomial. So 0.001 into, what is the derivative of x cube? 3x square minus 0.05 into, what's the derivative of x square? Which is nothing but 2x. Right. Again, what is the derivative of 7x? Which is 7, and derivative of 6500 is 0, since 6500 is a constant. Okay. So simplifying this, we will get 0.003 x square minus 0.505 into 2, so that will be 0.1 x plus 7. Right. So this is the general cost function here, and now we can find the marginal cost for the 14th unit by simply substituting x equal to 14. So this is the marginal cost function for x. So the marginal cost for the 14th units can be easily obtained by replacing x with 14. So which will be 0.003 into 14 square minus 0.1 into 14 plus 7. Right. So you can try to simplify this, and the result will be 7.8. Right. So the marginal cost for 14th unit is 7.8. This is how we use derivatives to find marginal cost. And the same can happen for marginal revenue as well. And the cost function or revenue function need not be always a polynomial. That can be a quotient, or maybe a quotient as well, or whatever. Whatever the function, we can use the rules we have been discussing so far to find the derivative, and the derivative will be the marginal cost or marginal revenue, as in the case. Right. So this is a simple example of a practical application of derivative or differentiation in a general sense in the field of economics.